Hey, what's up, guys? Something else that has been bugging me ever since I put in this super high pressure and flow coolant system is the fact that chips and coolant, they get blown everywhere. It's kind of cool because it washes out the bed. I mean, I open this thing at the end of a program and this thing is spotless compared to what it used to be. I mean, I used to have like aluminum shavings everywhere. I mean, now it pretty much all washes down to the back. But it blows coolant chips up into the tool changer. And like sometimes I'll get like a chip on the side of the taper. And when the tool change occurs and that tool goes up inside the spindle, it won't get a perfect seat. And the tool will have run out and it's just really not good for the spindles. So what I'm thinking about doing is adding a nozzle that blasts compressed air over the top of this tool change position at a certain point of the program to clean off this taper right before the taper goes up inside the spindle. So that's one of my engineering challenges I think I'm going to try and tackle over the next couple of days. Today we are going to use the milling machine as a water jet table. I need to cut a shape out of this plate of metal, and I'm gonna just profile it with an end mill rather than have it water jet because I'm too cheap and I'm too lazy to have it water jet. Actually, it's not that I'm too lazy. It's really, I mean, I have the material, I have the time, so I'm just gonna cut it on the mill. And I can modify the geometry if I need to. And what we're doing is we're putting an encoder on the top of the spindle motor. Now, if you're not familiar with what an encoder does, is it essentially counts pulses as a shaft rotates around. So I have I think a 3,000 pulse encoder, so it's gonna send 3,000 pulses every time this shaft moves around one revolution. And the reason I'm doing that is because I want to set up rigid tapping for this machine. If you guys have watched my other videos, you've heard me talk about how this machine is capable of doing rigid tapping, and all I have to do is set up an encoder on top of the spindle. And the encoder will essentially tell the machine how many revolutions the spindle has made with a great deal of accuracy so that the Z-axis can follow the spindle encoder down and make the correct change in elevation per revolution so that a tap will correctly cut threads and then back out of a hole without breaking. So that's kind of what we're doing right now. This is the hardware that I ordered from SDPI. I can't remember the name of the website, but they have drive pulleys and timing belt pulleys, and these are this is a toothed rubber belt, and it rides on this pulley, and then it turns this pulley at a 3-to-2 reduction. So every time this 2-to-3 increase. So every time this pulley will go around twice, this pulley will go around 3 times. Now, the reason I have to build this setup is because the software and the hardware needs to read an index pulse, and an index pulse it's a pulse that's sent from the encoder once per revolution. Now here's the encoder wheel. Let's see if we can get a better look at it. And you can't tell in the video, but the shaded region around the edge of the encoder, those are actually little bitty lines, and every time one of those lines passes underneath the optical, I'll call it a detector, but I'm sure there's a more sophisticated name for it, it will send a pulse. Now the index pulse only happens once per revolution, and it's right here. And the hardware uses this index pulse in the threading operation to, I guess, check RPM. And it has to be the RPM of the spindle, not the RPM of the spindle motor. So if I were to just throw this on top of the spindle motor, I would get this index pulse twice per every 3 revolutions of the actual spindle itself, and the Z-axis would change depth incorrectly and the tool would break. So I have to build this like reduction setup and then mount the encoder on top of the shaft that rides on this pulley here. So I have to machine a pillow block, or a block to hold these bearings. Then I have to machine a shaft that will ride through these bearings and then come through this pulley, And then on the bottom of the block, the encoder will mount. This is the encoder body here. And this has to mount on the spindle. And there has to be an entire plate to hold the entire assembly. So that's kind of what I'm building now. That's what I have that 3/8 plate bolted on the Matsuura for. I'm currently designing the geometry in a CAD program now, in Fusion. And then I'm going to cut it here in a few minutes. Because we don't really need to worry about repeatability, we're just going to kind of pick an arbitrary 0 spot. This will essentially center the part that we're going to cut out in the middle of this plate. We're not going to use the plate for anything else. It's pretty much just a throwaway piece for this particular part. So we'll just 0 off right about at that X there and press go. This is what it looks like when you use your machine as a water jet. Right away I noticed a problem that I had. This mark right here was left because I didn't set my tool retract in the CAM program. I essentially didn't tell it to come up above the material before it moved on to the next operation. Surface finish is pretty decent. I left some tabs, some 100,000ths tabs that I'm probably going to go back in the program and just have them cut those off, because those are actually a little bit beefier than I thought they would be. I thought I could cut them by hand, but they're really too thick. And I don't think this piece of material is going to go anywhere if I do cut them off. But yeah. Probably should have left our spacer underneath there. Okay. Decent. This will work. Just got some edges to clean up where those tabs were. Ideally, if this were a part for a customer, we would set up better fixturing, but this will definitely work to hold that encoder on the top of the spindle. Okay, let's see how she fits up. Okay, let's see how she fits. Oh no.
dropped a bolt, but it's looking like my measurements were spot on. Oh yeah, she fits up pretty well. Plenty of clearance between the spindle, base of the spindle shaft and the housing. Now I just need to machine up the block assembly to hold these two bearings and that pulley.
Okay, this is half of the bearing block assembly that's going to hold this pulley and the shaft and the bearing. This is where the bearing goes. Fits in there pretty dadgum well. This surface finish right here on the edge is rough, but it's a high-speed tool path, and I don't need it to be smooth. If you look at the surface finish inside this hole, however, though, it is remarkably smooth. Kind of hard to focus with a stupid iPhone. So that's half. This is the first iteration of it, which I screwed up, but essentially they go on top of each other, just like that, and the pulley rides in there, and the belt will come out. So that's kind of what it'll look like when it's done, and then that will bolt to the top of the plate that we just put on top of the spindle. So I finished the other half. It did not take long because the machine was already programmed. I just carried that pocket all the way through because the encoder will mount on the top here, and the shaft has got to protrude out the top. So one of the problems I have, I didn't even realize this until I got finished, is this is not exactly 2 inches wide. I remember now when I picked up this aluminum, he sold it to me pretty cheap because it was like 20 thousandths undersized. So if you look here at the wall, this is pretty thin. This is much thicker. Probably almost double the thickness on this side as on this side. Well, it's not a big deal until, so you machine both of them with essentially the same program except for this pocket, but when you flip it over, these sides don't line up. I can hold these together. You can look inside that pocket there. So this is with the sides lined up, and look at the misalignment between these two edges, and I really don't like that. It would work if I simply slid it over like this. The bolts would line up, the bearing pockets would line up, and all of the surfaces would mate, but the outside would have this lip that you can catch your fingernail on. And you know, it's really not that big a deal. It just irritates the crap out of me. It took forever to develop this tooling path.
You don't like these?
Well, feel it. There's a little bit of play in the bearing itself.
Yeah. Did you have to assemble like that?
Like what?
Like have a through hole?
Yeah, I have to have a through hole because the encoder mounts up here. So this has get turns down to, yeah. So here it is together with the mismatched sides. Inside it feels great. That seam lines up quite well. And this shaft spins pretty freely. The only problem is I have a complaint with these bearings. These bearings are just not real tight. They turn pretty easily, but they have a little bit of play in them. I mean, I can feel probably at the base here, I could probably feel a thousandth or two of side play, which is not going to be a big deal because the pulley will be down inside that pocket and will be pulling the shaft upwards or sideways, and have tension on it. So yeah, it's coming together. So we machined the shaft that sits on these bearings and that pulley rides on. Here's our pulley. One thing we also did was we opened this pulley up to a 1/2 inch so that it fits on this shaft. So this pulley will fit on the shaft. There'll be another bearing here.
this entire assembly will fit right inside here. Now I don't know if this will work, but I kind of want to keep these bearings in this pocket mounted snugly, so I'm going to use thread locker. And I have no idea whether or not that's going to work long term, but I'm going to try it anyway. A little bit on the inside here. It's way too much, really. We don't want it to get caught on any of the bearing surfaces that turn, so we just kind of want to dab on the outside edge of the bearing. That was a little too much. Feels like it's never coming out. Feels like it's stuck in there pretty good. That doing it. Some good butterfingers. These bearings are fit very snugly. Actually going to put some thread locker in the bottom of this shaft so it will kind of adhere to the inside of that bearing. It's really not important. Actually, I don't think we're going to do that. I'm too lazy. I'm going to lift this just barely off the base of this pocket so we have a little bit of clearance here. I'm going to tighten this guy down. This guy up. Got it backwards. This is our base.
You doing, John?
Isaac bored these out and they're pretty much perfect. I'd say that's about the height. Tell you what, that misalignment in that block just annoys the living bejesus out of me.
What misalignment? Oh, in the pulley block?
Now when I bought these two pulley setups in this belt, they gave me an exact dimension for center to center, and that's what I machined it to. There's no slots or method of tensioning. It's all machined to pretty much the center to center distance that the engineer told me. So when I put this belt on, it should be properly tensioned. It's a good deal of tension there. And from the way that's riding, I need to probably bring up that pulley a little bit more. Yeah. Feels great though.
You want me to get the mic so we can measure the height across this plate?
No, it's perfect right there. Just tell the way that it's riding. Just the right spot. I'm going to go down there and fire up this spindle.
Make sure the belt rides in the center.
Make sure it's not going to come apart.
I think we should probably start at a slow RPM, like 2,000.
No, I think we should go from start the highest RPM.
Uh-huh.
The goal is to get this entire assembly to explode. This reminds me of the work we did on your skateboard. I'll be right back.
ladder here.
Here we go.
It looks remarkably good, but the belt just rode up flush with the top of the pulley. I don't think that one is centered very well. The shaft doesn't look very good on that one.
This shaft has a lot of wobble too.
The actual shaft, yeah.
I think we should remachine the shaft so it's not wobbly.
It moves and quite a bit.
I'm gonna crank the RPM up to see what it sounds
Well, we want, yeah.
So we're really not happy with the sound that this thing made at 4,500 RPM. It sounded like it was going to come apart. Whee! And this thing needs to be able to run all day, every day. We're going to redo our shaft because the shaft we used was a piece of just stock 1/2-inch aluminum, and we didn't machine the shaft that went inside the bearing. We just machined the tip that went inside the encoder. So we're going to start with a 5/8 piece so that we can get a truly round and a truly centered assembly here. Another thing was the belt comes out of the block at a height that is just above the top of the spindle motor shaft. So we're going to shave off like 220 thousandths off the bottom of this, so the whole assembly will sit a little bit lower. So this is the final version of our spindle drive encoder reduction pulley setup. Actually, there is one more thing I'm going to change. I didn't end up buying a long enough pigtail to come off of the encoder, so I had to wire up these old control wires from the old controller. And these are obviously going to go. I'm going to get a new wire to go all the way down into the control box. But it's running right now at about 1200 RPM, and it makes absolutely, well, it doesn't make no sound, but it sounds pretty good. Very quiet, very smooth, no play in the belt, no vibration, no misalignments of the pulley. This shaft that we remachined fits in there and has maybe 1/1000th in play. So it does pretty well, especially with the tension of the belt on there. And I have the encoder wired up to the computer, and I'll show you that here in a second. So go into plug-in control in Mach 3, open up the CS Labs plugin, go to expansion modules and click the ENC, and you can see here that we get a good RPM reading, 1875 actually. That's more than 1200. And that is because our spindle overdrive is cranked up. Now, one thing I did figure out when I put this on was that my estimated RPM was much lower than my actual RPM, and it's actually, when I turn my spindle override knob to this position, I get an actual RPM of about 1,000. See, my RPM is 1,040. Another really cool thing that this encoder does is it reads the angle position. The angle position of the encoder. So if I stop the spindle here real quick. Let's give it an M5 command. Spindle stops. It reads the position of the encoder right here, and I can rotate that by hand. See, we'll rotate about 90 degrees. And it reads the angle. So this is pretty handy if you need to align your spindle for a tool change and you don't have a pneumatic dog lock out. So, that project is done. Now on to the next. Thanks for watching, and don't forget to subscribe.